Hi everyone, my name is Makumba Gerard of EduMath. In this video, I'm going to respond to one of the comments that was made on a video titled How to Use Newton-Raphson's Method in Finding the Roots of Simple Functions. So our friend asked this question here. Find a real root to the following equations using the Newton-Raphson method, correct up to 4 decimal places. Roman numeral 1, we have 2 sine x minus x equal to 0, and the second equation is x squared minus natural logarithm of x minus 12 equal to 0. He says, sir, my request to you, please make a solution video on this question. Alright, so we are going to start, and in this video we are going to first of all look at the first Roman numeral, finding the real root to this equation here, and the next video that we shall have will be looking at this Roman numeral 2. And even before we shall have the second video, you will be able to handle Roman numeral 2 on your own. Stick with me and we start. Solution. Roman numeral 1, we have the equation 2 sine x minus x equal to 0. So first we are going to select fx be equal to 0. This implies that fx is equal to 2 sine x minus x. Now they need us to use the Newton-Raphson method. We have that xn plus 1 is equal to xn minus fxn divided by the f derivative of xn. So we have a task to obtain fxn and f derivative of xn. So let's first of all go ahead and get f derivative of x. So we are going to go ahead and discretize fx and f derivative of x. So here we go. We have fxn is equal to 2 sine n minus xn, and f derivative of xn is equal to 2 cos xn minus 1. Substituting in this Newton-Raphson method, we have xn plus 1 equal to xn minus 2 sine xn minus xn over 2 cos xn minus. Next step is the LCM, because this is over 1. LCM here, you have xn into bracket 2 cos xn minus 1 minus, we are opening here brackets, this will be 2 sine xn plus xn, everything over 2 cos xn minus 1. Next step is we are going to open this bracket here. On the next page, we have xn plus 1 equal to, we are opening brackets here, we shall have 2xn cos xn minus xn. This xn has entered, multiplied that, it entered, multiplied that term, minus 2 sine xn plus xn, everything over 2 cos xn minus 1. So collecting like terms, we find that xn cancels out and we remain with our formula xn plus 1 equal to 2 xn cos xn minus 2 sine xn, everything over 2 cos xn minus 1, where that n is equal to 0, 1, 2, 3, so on. Now, this question demanded us to use the Newton-Raphson method. So we have got the formula according to the Newton-Raphson method. So in this question, we realize we were not given the initial approximation of the root. So our task is to go ahead and first of all locate where the root lies, and thereby we shall have to get the initial approximation. Locating where the root lies, we have that fx is equal to 2 sine x minus x. Now, since we are dealing with trigonometrical ratios, our calculator is going to be in radians because the angles we are going to deal with are going to be very small. So let's check on the values which are in the proximity of 0. So we have f of 1. This is going to be 2 sine 1 minus 1. When we press our calculator, which is already now in radians, we shall get a value which is 0.68294197. It is a positive value. Let's go on. F evaluated at 2. This is going to be equal to 2 sine 2 minus 2, which is giving us a negative 0.181405146. Alright? Now, since f at 1 is greater than 0 and f evaluated at 2 is less than 0, this implies that f1 times f2 is a value which is less than 0. Therefore, by sign change, the root lies between 1 and 2. Now, we have located where the root lies. So, we are going to use that interval within which the root lies to get the initial approximation. So, the initial approximation, which we can call x naught, is just equal to the average of the two end points of the interval. It's 1 plus 2 all over 2. So our x naught is equal to 1.5. That is the initial approximation of the root. Now, when you're using the Newton-Raphson method, it has to state when you stop. Let's say they would ask us to perform up to a certain number of iterations. But in this question, they haven't asked us to compute a certain number of iterations. So here, we are now going to base on the number of decimal places the root has to be up to. There, we are going to get the maximum possible error. So the maximum possible error is going to help us to determine when to stop. This is equal to half times 10 power negative 4. This 4 is the number of decimal places. So the maximum possible error or the standard error is 0.00005. Now, we observe that when it comes to computing the maximum possible error, we have 5 decimal places, 1, 2, 3, 4, 5. This again tells us something that as we are going to be working out, we have to be working with 5 decimal places, and then thereafter we shall correct our final answer to the 4 decimal places that are required. So let's get started and see how this works. Now we have the initial approximation. We have the Newton-Raphson's formula for this question here. We're now going to apply the initial approximation to get the first root. So our Newton-Raphson's formula for that equation was this, which we obtained sometime here. Now we are going to make use of it. When n is equal to 0, when you put n here, we shall have to get x1 being equal to 2, x n is 0, this will be x naught cos x naught minus 2 sine x naught over 2 cos x naught minus 1. But our x naught, which is the initial approximation, is 1.5. So we have x naught equal to 1.5. Replacing it here gets us the first root. x1 is going to be equal to 2 times 1.5 cos 1.5 minus 2 sine 1.5 everything over 2 cos 1.5 minus 1. So when you press our calculator, which is still in radians, this value is going to be equal to 2.07656. 5 decimal places is what we are working with, because the maximum possible error is to 5 decimal places. Now by inspection, the error, which is equal to x1 minus x naught, this error is not less than 0.00005. Okay, so that means we have to go. When n is equal to 1, let's perform the next iteration. We are going to put 1 wherever there is n in this formula, right? So we shall have x2 being equal to 2x1 cos x1 minus 2 sine x1 over 2 cos x1 minus 1. Now, we got x1 from the previous iteration, so we are going to use this value of x1, which is 2.07656 in here. So substituting x1 in this formula here, we shall have to get 2 times x1, which is now 2.07656 cos 2.07656 minus 2 sine 2.07656 over 2 cos of 2.07656 minus 1. Pressing our calculator, which is still in radians, we get x2 as 1.91051, 5 decimal places. By inspection, we also realize that the error x2 minus x1 is not less than 0.00005. So that means we have to continue to the next iteration. When n is equal to 2, we shall have to get x3, which is equal to now 2 times. When n is equal to 2, we put it here, put here 2, we shall have to get x3, put here 2, we shall get x2. So this side we shall have to substitute their x2 accordingly. So let's do the substitution directly. This will be 2 times 1.91051 cos of 1.91051 minus 2 sine 1.91051 over 2 cos 1.91051 minus 1. So computing our x3, it is equal to 1.89562. That is our x3. Computing the error to determine if we have to stop or not, we only stop if the calculated error is less than the standard error. So error is equal to x3 minus x2, which is equal to the magnitude of 1.89562 minus 1.91051 and a magnitude. This is giving us a value which is 0.01489. This value is not less than the maximum possible error, which is 0.00005. Meaning we have to continue to the next iteration. When n is equal to 3, there that means we are going to get x4, which is equal to 2 times, we are now substituting directly x3, 1.89562 plus 1.89562 minus 2 sine of 1.89562 all over 2 cos of 1.89562 minus 1. So when you compute this value on our calculator, x4 is equal to 1.89549. When you look at these values, x3 and x4, they seem to be so close. We can't just conclude that the error between them is less than 0.0005. So that means we have to go ahead and check for the error. So error is equal to x4 minus x3, which is the magnitude of 1.89549 minus 1.89562 and a magnitude. So this is going to be equal to 0.00013. This value is not less than 0.00005. Here we can see clearly that these are 5 decimal places and these are also 5 decimal places. Now, since this calculated error is not less than the standard error, means that we have to continue to when n is 4. When n is equal to 4, we get here x5, which is equal to, I'm going to make direct substitution. This is 2 into brackets 1.89549 cos 1.89549 minus 2 sine of 1.89549, everything all over 2 cos of 1.89549 minus 1. Again, with our calculator in radians, we have to compute x5, which is equal to 1.89549. When you look at x4 and x5, right, they are the same values, meaning that our error is 0 this time. Let's see, error is equal to x5 minus x4. This is equal to 1.89549 minus 1.89549. So the error here is equal to 0, and 0 is less than 0.00005. Alright, so since our calculated error is now less than the standard error or the maximum possible error that should exist, then therefore we should make a conclusion and say the real root is 1.8955, and this is to 4 decimal places. So in numerical methods, we always work with 1 decimal place ahead, and then we go ahead to round off the final value to the required number of decimal places. Why we do that is because we need to compare very well with the standard error, and you cannot compare values with different degrees of accuracy. So here we are creating the same degree of accuracy. That's why we work with 5 decimal places, and then later on we round off to 4 decimal places. So that has been the working for Roman numeral 1. Please, my viewer, you can now go ahead and do the working for Roman numeral 2. If you are new here at EduMath, please consider subscribing and hitting that notification bell so that you are notified whenever we make a new video. For now, from us EduMath, we wish you the best and God bless you.